Let us study angular momentum revisited. Actually, in last semester, we have completely studied this part, and this is a review, so details can be found in the X series. So, my explanation in this lecture will be very brief. Kinematic variables of rotation. In the linear motion, we use x, velocity as a derivative, and acceleration as a double time derivative of position. In here, when we consider rotation, there is an axis of rotation along a unit vector n hat, and a particle has a position vector x whose tail is at a single point along this axis. So the rotation will generate a motion, but there is a strong restriction due to the fact it is this vector x is on a cone. The angle theta is introduced, and we have a theta vector is along the axis of rotation, and azimuthal angle measured from a certain direction, x-axis, E1 hat, something like that. From this axis, azimuthal angle is measured as a theta. The velocity, angular velocity, is the time derivative of this angle vector. We assume, in general, this direction may also change, but in general physics, we consider the case when the unit vector along the axis is fixed. There is something wrong. Oh, no. You will find in the next page the velocity of this object is tangent to the circle that is perpendicular to this axis of rotation, and this velocity x dot is nothing but the omega cross x. Here omega is theta dot. So we say it is angular position, angular displacement, angular velocity time derivative, angular acceleration double time derivative. Rodriguez rotation formula is very important to study the angular motion. Axis of rotation is invariant, assumed to be invariant, and this component is the vector's component along the axis of rotation. Any component along the axis of rotation is invariant under this rotation. The only contribution is perpendicular component. That perpendicular component at a certain time, this is a longitudinal component that is parallel to the axis, and original vector subtracted by the longitudinal component is the transverse component. You know this n hat and x per nx, and this is x parallel, and x per. This is before the rotation. After the rotation about a finite angle theta, This one is invariant, but this component decreases by a multiplicative factor cosine. An additional direction that is perpendicular to the perp direction as well as the axis of rotation. That new direction appears, and that amount is sine theta multiplied by n hat cross x. N hat cross x is this vector. So, if you make use of this Rodriguez rotation formula, the time derivative, the angular derivative about theta at theta equals 0 has non-vanishing value only along the perpendicular direction, that is perpendicular to both longitudinal and perp. So we assume that it is E3 and E1, then we have a new component along E2. That from which, because there was this cosine theta derivative is minus sine theta, and at theta equals 0, this vanish. This is constant derivative with respect to theta vanish. Only this component survives. And that one becomes a theta dot cosine theta if we compute the time derivative by chain rule. We end up with the fact theta dot n hat is called the angular velocity omega. So many cases we write it omega cross x. And because x parallel cross omega is always a 0, omega is along the n direction and x parallel is always along the same direction, cross product vanishes. Therefore, omega cross x is always the same as omega cross x perp. Centripetal acceleration can be computed by repeating the time derivative. We compute the time derivative twice. Effectively, time derivative is to be replaced with omega cross. So we carry out cross product twice. Then we can make use of back cap rule. We obtain this. And as you know, x perp direction. And we have negative direction. What's that? The direction is along the x perp? No, minus x perp. So if it makes a rotation, centripetal acceleration is toward the center. Tangential acceleration is also possible if theta, magnitude of theta dot, is not constant. Constant, then uniform circular motion. However, if theta dot is not constant, theta double dot is not vanishing, theta double dot is omega dot, and omega dot is also written as alpha, that is called angular acceleration. Hence, angular acceleration is written in this form. Again, we assume that n is fixed. If a particle is rotating about the fixed axis and hat, the kinetic energy can be written in a simple form. First of all, velocity of a particle is omega cross x. We square, then we find a similar structure as we just have obtained in here. That gives x perp squared. You can see x perp squared multiplies by theta dot squared. So in here, 1/2 something theta dot squared. 1/2 mv squared, that is x dot squared, is a normal kinetic energy. This rotation kinetic energy has dimensionless velocity, that is angular velocity squared. Because the length dimension has disappeared, that dimension is now included into the mass x perp squared. So the total dimensions are the same. Instead of mass, we have mass times lever arm squared. That is called rotational inertia when we sum over all of the particles inside a rigid body, a system of particles that are rotating all together. So just like 1/2 mv squared or p squared over 2m is used for the kinetic energy of a single particle, for a rotation of a rigid body, we use 1/2 I theta dot squared or 2I L squared, where L is the angular momentum I times omega. Here P is the linear momentum, mass times velocity. So rotational inertia has a structure mass times lever arm squared. Orbital angular momentum. Orbital angular momentum L equals I omega or theta dot, that can always be expressed as m lever arm squared multiplied by I. So the theta dot. And if we rewrite this one, we can find that it is x cross p. Detailed calculations are given in here. Rotational version of Newton's second law is to take the time derivative of angular momentum L, that is x cross p. If you take the time derivative of this one becomes velocity, and that contribution disappears. Only the contribution from the derivative of the last factor survives, and mx double dot is nothing but the force. Therefore, time derivative of angular momentum is torque, that is defined by x cross f. What happens if we collect many particles in a system and consider the sum of angular momentum of each particle? Then it can be written in this form. The total angular momentum can be expressed in the center of mass frame, at which the center of mass is at the origin. Then the computation becomes quite simple. The final result says that total angular momentum of a system of particle is xcm, center of mass, and the total linear momentum of the total system plus mv x cross p, x cross p. Here p is mx and there are many particles. However, we can see this bar. Angular momentum measured in the center of mass frame. So at the center of mass frame, this guy disappears because xcm is exactly 0. So at the center of mass frame, the total angular momentum reduces into this form, and x bar vector I is xi vector subtracted by the center of mass position vector. Rotational version of Newton's laws of system of particles. We recall that self-interaction does not exist because of this Newton's third law of action and reaction. So if we consider the net force on a single particle in a system, the net force consists of the sum of two. This one is external force coming from other particle in the system. This is internal force coming from other particles. Other means J is not equal to I. Total net torque can be computed by using this formula. We have external force contribution to the net force and internal force contribution. If we sum everything all together, then there are contributions from I to J and J to I. Because of the Newton's third law, we have opposite sign. In that case, xi subtracted by xj cross fj to I sum should be computed. If the internal force is central, that means it is parallel to the direction of the relative displacement. Then this contribution vanishes. Therefore, the net torque on a system of particles is the same as the net torque due to the external force if the internal forces among the particles inside the system is central. Angular momentum conservation derives from these results. Net torque is only due to the external torque on the whole system. If there is no net torque on the system from external sources, then total angular momentum must be conserved. Rotational version of the work kinetic energy theorem is essentially the same as the original work kinetic energy theorem. Here, we compute the change in the kinetic energy due to the rotation. And this one comes from this integral, and this is, we can find that this can be expressed as a total differential, integral of a total differential. By the way, the word torque, this is a torque angle scalar product. Change in rotational kinetic energy can be computed like that. What's that? The torque angle scalar product. So this is the proof of work kinetic energy theorem for the rotational motion. in the remaining part, I would rather ask you to review all the details about the calculation of rotational inertia from X series. I don't want to repeat all the, they are all the same. You have to remember how to compute the rotational inertia by integration. Kinetic energy of a rigid body can be expressed as a kinetic energy sum of the kinetic energy of the point particle whose mass is the same as the whole system with the velocity of the center of mass plus internal kinetic energy. The internal kinetic energy is measured, you know, this bar means relative to the center of mass. If the center of mass, you are describing the system at the center of mass system, then this term disappears and only the internal contribution survives. In the case of a rigid body, this internal kinetic energy can be computed quite compactly by making use of the rotational inertia. These are the examples, and please review these questions. That's it.